Okay, well, we can skip this one because we've already seen it. So, next one. Alright, so cosmic dust, what is it? And where do we find it? Well, maybe if you're lucky enough to look at the Milky Way, you need to be in a very dark spot, so here in Leiden that's not going to work. But perhaps if you've been in the Ente, for instance, in the Netherlands, or an even darker spot, maybe where these big telescopes are, in Chile or in La Palma, you might have seen the Milky Way. And if you look at the Milky Way, you first see like a number of stars, like millions of billions of stars, but there are also these dark patches that you see over here, and that's all interstellar dust. Oh, next slide, please. So these dark patches, they're seen by people for ages, and they stood out quite a lot, but it wasn't until like the 17th, 18th century then telescopes really improved, and people were really able to see these dust clouds in more detail. And someone who saw them was William Herschel, and so he looked at a number of these clouds, and particularly the dark nebula here in Scorpius. And what he said, well, there is really a hole here in the sky. And his sister, Caroline Herschel, was actually so surprised by this comment that she saw it again in the notes and went back and asked William Herschel's son, John Herschel, to look at it again. So they observed these clouds again. And they weren't really sure what they were, but they were sure that this was not a hole in the sky. So it took a while before people started to realize that this is actually foreground material obscuring the stars behind it. And if these clouds are dense enough, you actually don't see the stars behind it anymore, and it appears like a hole in the sky. So what is this dust then? Or what is it made of? And I like to think of it as dust is the spice of the universe. So there's this really nice example of a friend and colleague of mine, Daniele Rogantini. He compared the Milky Way to a pizza. So this is the pizza galaxy. And on top of the pizza, there is mozzarella. And the mozzarella is the interstellar medium of the galaxy. And it means this is all the gas and dust that there is in the galaxy. So this mozzarella is only 1/5 of the Milky Way pizza. So it's not that much, but not that little. Now, cosmic dust is just 1% of the galactic mozzarella. So it's only a little bit. So you can think of it as the spice you sprinkle on top of the pizza. And he also said to me, please tell him that the Milky Way is pineapple great. Anyway, so why does dust really live up to this spice of the universe? Well, that can be seen here. So dust really spices up the life cycle of stars. And it starts, well, my story actually, it starts here at old stars. So old evolved stars, they're starting to lose a lot of mass. And these stars, they are responsible for all the elements that we know and we were made of, actually. So pretty important. And when these stars evolve, they start losing this mass and returning it to the interstellar medium, to the space between the stars. And there is material can form clouds, like these diffuse clouds you see over there. And if these clouds become dense enough, dust actually shields the inside of the cloud and ensures that it can cool. And when the cloud can cool, it can start to contract. And if it contracts enough, and if it's heavy enough, if there's enough mass, it can collapse and form stars. And then this dust, and all the leftover material that doesn't go into this new star, can be used to form planets. So that's shown over here. So this is a very young star with an accretion disk around it forming planets. Then you can look at a mature stellar system like ours, and the whole cycle starts again. And in each stage, dust is important. So, but what is it? What is cosmic dust? Well, we found that there are mainly two groups. So there are carbons, soot or smoke, and these particles are very, very tiny. So that's why, you can compare them to these smoke clouds. And then there are silicates, And yeah, you can compare them to beach sand, like I look over here, but the particles are much, much smaller than that. And if you are in a very dense environment and very cold, you can also have ice layers around these particles. But the main components of these silicates are oxygen, silicon, magnesium, and iron, and for carbon, obviously carbon. So you would say, well, that's great. That's also actually the main components the Earth is made of. So, well, problem solved, right? We know everything already. We know what the Earth is made of. We know what interstellar dust is made of. So that's it. Well, no, actually, no. We have so many questions about interstellar dust. For instance, how does dust form and where? So I told you about this story about the life cycle of stars, and let me think that dust freezes out here in these old, in the atmosphere of these old stars. We're not really sure about that. It might get destroyed here in the interstellar medium. It's not a very nice environment to be in. There's a lot of radiation, shocks from supernovae, as is shown over here. So yeah, we are not really sure where it forms, if it gets destroyed in the interstellar medium, or yeah, if it actually grows there. And then, what is the composition of this dust, and is it in particular the same everywhere in the galaxy, or is it different? And you can imagine that's quite a big impact if the dust is different in different parts of the galaxy, because do planets form in the same way then, or do they look completely different? And what about other galaxies? Maybe dust is different in other galaxies. And then we are missing a lot of elements actually. For instance, well, actually in particularly iron. There must be a lot of iron. We know that the core of our planet is made of iron. We are not really detecting it very well in the interstellar medium. Yeah, and then why is there dust at all? So I already told you that we don't know where the dust is formed exactly, but why is it not completely destroyed by all these supernova shocks, cosmic rays and radiation? We simply do not know yet. Okay, but how do we solve these questions? How do we look into this? We can study the properties of dust. So you can imagine, if you look at the grain sizes of these dust particles, we know if they got destroyed or if they are growing. So that's something we are particularly interested in. Then crystallinity. So if dust is produced by stars, quite a large percentage, up to 15, maybe even 60% of it is produced in crystalline form. And what do we mean with that? Well, it has this nice structure. So this is quartz in a crystalline form, but you also can get it in a very irregularly glassy form if it got in contact with radiation and stuff like that. So then you get this irregular pattern. And then of course there's a chemical composition that we can also study. Okay, so how do we do that? Well, very simple picture. We look at the galaxy, we look at stars in the galaxy, and we look at clouds of dust and gas that are in between us, here at the telescope, and we look at everything that gets absorbed and scattered away from our line of sight. And in the optical, it looks like this. So imagine here you have a very blue star. So here there is no dust in between you and the star actually. But here on the other side, here is a very reddened star, so here there's a lot of dust in front of you, and all the blue light is scattered away or absorbed. So that's one way of looking at stars, but this is only in a very small wavelength band, of course. So this is the whole spectrum, and I was just talking about this little part, the visible part, but there is so much more to explore. And some wavelengths really show you the composition, the grain size, and the crystallinity of particles. And particularly interesting for that is the infrared and the X-rays. So the X-rays you've probably all heard of, so you can nicely see your bones. You can also really nicely look at the properties of dust. And here's the infrared, so this is actually me in infrared radiation. go to the old observatory to get your picture taken in infrared. It's really cool. So you can see parts that are colder and hotter here of your body. Also, interstellar dust particles can get warm, hot. They start shaking a little bit, and we can detect that signal, and we can infer from that a lot of the properties from dust. Alright, so we do have to go to space for this. These imprints on the spectrum are very tiny and very difficult to observe. So for that, we have infrared telescopes. This is Spitzer. We now also have JWST, which is very, very great for that. And we have two very, very nice X-ray telescopes called Newton and Chandra. And so actually, the X-ray field of studying interstellar dust is quite new, relatively new. It's like about 20 years old. And in the infrared, we've been doing this for a little bit longer. Anyway, let's continue. We also need to compare these spectra from stars with dust models. How do we do that? Well, we first need to collect these dust models. So that's what we did in the past years. First in the infrared and then for the X-rays, but it's the same material. So you can collect stuff from dust from meteorites, from synthesized dust from the lab, so especially made to resemble space dust, cosmic dust, and natural samples from Earth. And we crush them to a fine powder, and we put them in a radiation beam. Here you see a laboratory measurement in the X-rays. We do a similar thing in the infrared. Then we make dust models out of that, and we compare them with observations. So some results from models and observations. So for the infrared, it's a similar story as I told you in the beginning. We find these silicates, we find the carbonaceous dust. Great. Then we move on to the X-rays. And actually it's a little bit different. So we see in the center of the galaxy, we see silicates, but in particularly one species. We see a lot of olivine in the center of the galaxy, which is pretty interesting. That is just one kind of species. So olivine is quite an interesting material, and it's been in the news a lot, and maybe you've heard about this, but it can be used to for the CO2 reduction. So what you can do is crush this to a very, very fine powder, actually, like we did in the lab, and then throw this in the ocean. So with water, you get this reaction, and you end up with magnesium, something that looks a lot like baking soda, and silicon dioxide. So this is actually probably the reason why we didn't feel the harm of CO2 for a long, long time. Because the oceans were able to capture a lot of these and store a lot of this CO2 for a very long time. So it's an interesting material. Okay, but there's more. So I already told you we can't find iron. Well, X-rays are very nice for that. So we can actually detect iron in the interstellar medium, in grains, in a galaxy. But not all our questions are solved, not by far, because crystallinity is still a very, very big question. In the infrared, only 1% of the dust, like roughly 1%, is crystalline. So we always thought like a lot of this dust gets destroyed. Well, in the X-rays, we find much more crystalline dust, like up to like 15% of it, which is actually what stars roughly on average produce. So it's nice to still have questions, right? Okay, and we have a lot of new, nice upcoming telescopes to solve these questions. PRISM is an X-ray telescope that will be launched in August of this year. And then we have new Athena, also an X-ray telescope, will be launched in the 2030s. And currently, already observing dust in the infrared is James Webb. And so there's much more to come. And that's it. Thanks.
Are there questions in the session? some samples from space to actually build your dust models. How do you cope with like oxidation of the sample or the contamination of the sample when you bring it back on Earth?
So actually, we don't use interstellar samples that were in a protected environment. And most of the stuff that we need to use under protected atmospheres is made in the lab, especially, because it's impossible to do so. It would be interesting to use, for instance, materials from the Hayabusa mission, because they really capture that and keep it in a protected environment. But for materials such as olivine, it doesn't react with anything, so you can just make it from a meteorite and use it. Anything with iron sulfide, that oxidizes. And we once went to the lab and thought we had a nice sample, and we opened the box. And there were huge peaks in the spectrum of oxygen, and we could throw the sample away. So that happens, yeah. Thank you.
Other questions?
So at ESA, we are a little bit involved in it, and I, together with a lot of people at Astron actually, because they are very involved in that. Astron is also here in Leiden Space Institute. And they built some of the instruments, and yeah, it's going to be very interesting to compare all our dust models that we have with the upcoming observations. Yeah, the first thing we do from that will probably be like 2 months after the launch, so it will still take some time. But yeah, we are all very excited for August.
Any other questions? Yep.
I was wondering what got you into space dust? Why is it something that fascinated you at the start?
Oh, why dust? Yeah, that's a good question. I think because you can really touch it, right? And actually, I forgot to show you that, but there was one picture on the slides that was actually interstellar dust. So some of these grains fall on Earth like in the form of meteorites, or you can capture them and you can actually trace them back to the interstellar medium. So it's something from space that is really literally solid, and you can study on Earth. So I think that's what attracted me a lot in this kind of research. And the very interesting and I would almost say romantic thought that we are made of this stuff, and we want to know why we're made of it and how it came to be.
Thanks.
Any final questions? Okay, if not, let's thank Sascha.